Kia ora koutou, Reese from QuickSense here, and today we're looking at congruent shapes. Now remember, when we use the word congruent in geometry, we mean that the shapes are the same. So they have the same size, but they can be flipped, they can be rotated, right? So I could do anything to it other than kind of shrinking it or increasing it. So that's what we would refer to as a similar shape. But congruent shapes, it's the same scale, right? It's the same size. If I were to rotate it, it would look the same. So with these ones here, we're looking for shapes that through rotation, reflection, or moving it about, but none of these are actually moved about, we can make it the same. And I can immediately see actually that, right, we've got this shape here. And so I'm going to see if I can map that onto anyone else. I can see down here, I have that same shape there, but I am rotating it, right? I'm taking this first one and rotating it clockwise 90 degrees. Now I'm going to look for some other shapes. We can see with 2, right, it doesn't have, right, 2 kind of goes up like this, right, and 1 doesn't do that. So 1 and 2 are not congruent. And we can see with 3 as well, right, what does 3 do? Well, it comes straight down. So 1 and 3 aren't congruent. Looking at 5 here, well, 5 is very similar to 1, except that they are reflected, right? So same shape, but it is reflected. So which ones are congruent? Well, 1, 4, and 5. In this next question, we are given some coordinates of a parallelogram and asked something about a congruent parallelogram with some of the coordinates given. Now, immediately what I want to do is to get a better picture of what these parallelograms look like. So I'm just going to draw them on a grid. Now, it doesn't need to be an amazing grid. It can be pretty rough, right? And we can make this better. So we can have a look at, well, exactly 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. And we're going to need to go up to 5, so we'll go right up there. 1, 2, 3, 4, and 5. All right, so I'm going to start mapping A, or my first parallelogram, onto this. So A is -3, -3, 1, 2, 3, and then down 3. So this is A. B is 1 -3, so over here. C is 2 -1, over here. And then D, -2 -1, is over here. So now I can join these up and you can see this parallelogram. Well, what's happening with the other one? Let's just make sure that this is a little bit clearer. Okay, so we're mapping those. Well, the next one we have, again, we're going to map it. So A moves to 0, 1. Okay, well, that's one of the ways we're thinking about, right? Perhaps this is happening. So let's have a look at that. 0, it goes up 1. 4, up 1. 5, 3. And then there's 1 left over. Now, if you're anything like me, you're probably thinking it's going to go there, right? How else can I turn this into a parallelogram? Well, before we do that, we need to just double check, right? If we're assuming that it's just been shifted, are we doing the same thing to every single point? So what do I mean? Well, what I'm saying is, does the move from A to here, to A1, correspond to the move from C to C1, or B to B1? Well, what is that move? For A, let's do this in green, we're going across 3 and up 4. So let's call that from A to A1, across 3 and up 4. Well, what's happening from B to B1? Well, again, 1, 2, 3, and then up 4. Oh. And finally, let's have a look at C here. 1, 2, 3, up 4 again. So I'm pretty confident that I am shifting this by 3, 4, in which case D, which was -2, -1, becomes -2 plus 3 -1 plus 4, which is equal to 1, 3. And in fact, that is exactly where we thought it was. Okay, so what is the coordinate of the fourth vertex of D or D1? Well, it is 1, 3.